All right, hi guys. We're talking today about 1.3, properties of limits. So in the last section you learned basically what a limit is, definition of a limit, how to find a limit, both graphically and numerically. And today we're going to talk more about how to find it algebraically, okay? And so what you've learned here, and you can kind of read through this, we've learned that the limit of f of x as x approaches c does not depend on the value of f at c, at x equals c. It could be the same, it could be different, it doesn't have anything to do with it. It's about what it's approaching, right? But sometimes the limit is actually equal to that value, that y value, f of c, whatever that y value is. It might actually be equal to the limit. In such cases, we call the limit can be evaluated by what's called direct substitution. This is always going to be your first attempt to find a limit, is you're always going to start with this method of direct substitution. This is going to be the easiest thing. So if it works, great. You don't have to do numerical or graphical, or you could just to support your answer, but it's not necessary. And so you really want to try direct substitution first and see what happens. Now, if it's a nice, well-behaved function, we call these well-behaved functions, just like all of you, you're such well-behaved students. They're called continuous functions at C. So your graph is continuing through C there. So these are for some basic ones, some basic limits here. Like if you have the limit as x approaches C of a constant, it's just going to equal that constant, right? If that's a number, like 3, your limit will just equal 3, right? That's just a horizontal line. As x approaches anything, any c value, it's just going to be 3, right? For the graph of y equals x, then as it approaches c, that's just direct substitution, so you're just going to get c, because y is always equal to x. So whatever your x value is, that's what your y value is, and therefore that's what your limit is. For the limit of a simple polynomial, x to the first, x to the second, x to the third, whatever it is, again, it's just that direct substitution, and it becomes c to the end, so whatever that power was originally. And so if you've got some basic limits like this one, again, it's just a constant term, so that's just going to equal 3 no matter what. For this one, as it's -4, we're going to plug it in there, and we'll just get -4. Here, we'll plug in the 2, so 2 to the second is just 4. All right, so again, you're noticing this direct substitution method. And we'll talk about what happens if direct substitution doesn't work. But if direct substitution works, you always use it every single time. So for basic things like these, like nice polynomials, nice rationals, nice quadratics, things like that, you can just do direct substitution. So I'll plug it in, 5 times 3 squared, and I get 45. Here you plug it in everywhere you see an x, right? So that gives me 6 plus -2 minus -2 squared. So what is that? 4 minus 4, just 0. Double check my math. If I make a mistake, let me know. Here I'm just going to plug it in. I've got a linear function times a quartic function. So I'd plug in 1 times 3 times 1 to the first, which is just 3. Here, same thing. I'm going to plug it in both places. So I get 5 plus 3 over 5 minus 2. Right, and you can obviously figure all these out. So these are nice direct substitution. You're just plugging it in, and you're not having any problems, right? It's when we start having problems that we got to do something else. So that one was just 81. Okay, so that's where it talks about here, the limit of a polynomial. If this is a nice behaved polynomial, you just have to do direct substitution. 4 times 2 squared plus 3, is that 19? So it's just simply the value of p at x equals 2. It's just plugging it in. It's direct substitution. It's equal to that value. This direct substitution property works for all polynomials and rational functions that don't have 0 in the denominator. Okay, so you're going to see it does work for a lot of functions. And as you're doing the homework, you're always going to start with direct substitution. You're going to notice that it will work for a lot of these. Okay, so let's keep going here. All right, example 3, let's try direct substitution, right? So I'm going to plug in a 1 here, plug it in here and here, and let's see what happens. 8, 2, 3, so that gives me 4 which is just 2. So that worked nicely. Okay, so again, if it's not making the denominator 0 and it's just working out pretty nicely, you just do direct substitution. This is easy, right? Who said calculus was hard? This is nice and easy. So let's try here. I plug in a 0, 0 squared plus 4. That's just 4. I plug in a 4, the square root of 4. This is principal square roots, which is positive 2. When I plug this in, then it would just be the square root of 4, which would be 2. Okay, this is the composition of these two functions, right? So if you can find the limit of each, you should be able to find the limit of their composition. But again, I just want you to focus on, you know what? I'm just going to try direct substitution. Okay, and so what would this be? 9, 18. Oh, so the cube root of 8 is just 2. All right, so again, just get into that habit. This even works for trig functions, right? If the trig function is well behaved at that point, then it should work fine. So now we're going to plug this in, so that gives me the tangent of 0. Uh-oh, got to go back to trig. So go back to your unit circle. Here's 0. My gosh, I know. Can you believe I'm doing this? 1, 0. So tangent is y over x, or sine over cosine. So that's 0 over 1. So tangent of 0 is 0. So that works out nicely. All right, let's try this one. This is pi. Sorry, it's kind of blurry if you can't see that. So it should be pi times the cosine of pi, right? So what is the cosine of pi? Well, let's go back over here to my unit circle. Pi is -1, 0. Cosine is my x value, so that's just -1. So it's pi times -1. So my answer is just -pi. All right, let's try this one. So this is the sine of 0 squared. Well, again, if I go back to 0, my coordinates are 1, 0. So sine is just 0, and 0 squared is just 0. So again, well behaved, there's no issues, so we can just do direct substitution. Okay, so this is how you do algebraic limits, right? You first always try direct substitution. Okay, and try and recognize some of the ones that are going to work, like a polynomial, a nice rational, a nice radical, some composite functions, some basic trig functions. Those are going to work nicely, right? And so you can just do your direct substitution. So the question is, what if it cannot be evaluated by direct substitution? So now I'm going to show you some examples like that. If it doesn't work, like you get a 0 in a denominator, or you get a negative under a radical, right? These weird things that show you errors or undefined, stuff like that. Then what you have to do is try and find some other function that agrees with f for all other values. And what you're going to see here is this is the situation where you find a hole, usually, for our rationals, right? You guys are used to kind of seeing the rational graphs, so you'll see what happens there, right, with the rationals and the holes, and that's usually what we're going to see there. And then you can always go back to graphs or tables, so you can go back to numeric or graphical to reinforce what you've figured out, right? So if you think maybe that the limit is 7, let's say, well, if you're not 100% sure, always go back to the graph. You'll see I do a lot of that, just going back and checking the graph, making sure it makes sense graphically or numerically to figure it out from there. Okay. All right, so let's look at an example. This will be some examples now where we're in like situation 2, where it can't be evaluated by direct substitution. So watch what happens here. If I take this 1 and I plug it in both places, I'm going to get 1 cubed minus 1 over 1 minus 1. So that gives me 0 over 0. Ah, bad news, right? We cannot have this 0 in the denominator. And so this is our big issue here, right? You can never have a 0 in a denominator, and you're not just going to write undefined as an answer. What you have to do now is do some work, or you got to do something. You have to go back to the original problem, and you have to somehow manipulate this original problem. Usually it's going to involve factoring, canceling, right? Simplifying that expression somehow. You need to somehow manipulate this, again, using factoring, canceling something out, simplifying. Sometimes it helps to do something like rationalizing. Okay, so these are all techniques that you're going to use to try and see how I can rewrite this original equation in a different way that then I'm going to try direct substitution and see if it'll then work after I've tried one of these techniques to manipulate it a little bit. Okay, so let's go back to the original and start over. So it was the limit as x approaches 1. Now, x cubed minus 1 can be factored, right? So let's factor that. So do you guys remember how to factor a difference of cubes? Right? So the first one's a binomial, x minus 1, same, opposite, positive, and we still have that x minus 1 on the bottom. So what happens? Well, those x minus 1s disappear. And now I'm just left with the limit as x approaches 1 of this quantity, x squared plus x plus 1. This is what was left on top, right? Now I'm going to try direct substitution. Maybe it'll work. So let's plug in the 1s, and I'll get 1 squared plus 1 plus 1. 1 plus 1 plus 1 is 3. And that is my answer. So after I've done a little manipulating, canceling, simplifying, rationalizing, whatever it is, in this case it was factoring and canceling, I now have a similar equation that behaves the same way, but I can now take that limit by doing direct substitution. Okay. Graphically, what's happening here, right, if you think about this graph, is we have a hole at 1, 3. Okay, and this graph I think looks something like this. I don't know, it's something like this. It's a parabola, but it's a big parabola with a hole in it. Okay, and what's happening is I'm asking for the limit right there as it's approaching from both sides that x value of 1. And so what's the limit? Well, the limit is the y value of 3, because from both directions it's approaching 3, right? When I go to my x value of 1, my y value is approaching 3, so 3 is my limit, right? So you can back it up graphically, or you can just do it algebraically. All right, so that's the idea of if it doesn't work with direct substitution, you're going to do this manipulation. So let's try another one. You can kind of right away see if I try this -3, I get -3 plus 3, and I would have 0 in the denominator again. So, can't do it, not a good idea. This is similar to the last example where we can factor. Okay, so let's go ahead and factor that. The limit as x approaches -3. I'll factor it into x plus 3, x minus 2, right? The x plus 3's are going to cancel. Now I'm just left with the limit as x approaches -3 of x minus 2. This is all I'm left with. Try my direct substitution now. -3 minus 2, and it works. Ta-da! So that is now my answer. After factoring and dividing it out. Okay, so after I've simplified it, it works. So let's try this one. This is a rationalizing technique. Again, if you try to direct substitute right away, you're going to get the 0 in the denominator. Can't have that. So we need to try something else. So that equation looks like this. Square root of x plus 1 minus 1 over x. This one's a little interesting, you guys. The way you're going to do this, and you've never done this before, is instead of rationalizing a denominator, guess what you're going to do? You're going to rationalize the numerator. How about that? All right, just because the radical's in the top. So you can really rationalize either one, but since the radical's in the top, I'm going to rationalize the numerator, which means I'm going to multiply by its conjugate. So instead of a minus, it's plus, and I do that same thing on the bottom. Okay. My hint is that on that denominator, I am not going to distribute it out. I'm just going to leave it. On the top, remember when we multiply conjugates, you only have to do first and, whoops, not that one. You only have to do first and, not outers and inners, but then first and last, right? Because the outers and the inners always cancel out. So when I multiply those two first ones together, I just get x plus 1. The radical's gone, and then it's minus 1. Haha, watch this magic, right? Isn't that cool? So the plus 1 and the minus 1 disappear, and I'm left with an x on top, and an x and this whole thing on the bottom. And notice the x's disappear. And now I'm just left with, sorry, I'm running out of room, 1 on top over this whole expression on the bottom. But remember, we were taking the limit as x approaches 0 of this whole expression. So now I need to try direct substitution and hope that it works this time. So I'm left with 1 over 0 plus 1 plus 1. So that's 1 over square root of 1 is 1 plus 1. My answer worked. So I ended up getting a number 1/2, and I didn't have to do any other work, right? So that's this cool technique called rationalizing the numerator. It's the same thing you would have done before when you rationalized a denominator. It's just rationalizing a numerator again, okay? So a little different, but same idea. All right, I have 2 more examples, and then this will be it. So this next one, example 9, you can rationalize this numerator if you want to. Totally, it'll work. And in fact, I can show you both ways. But there's another way that if you recognize that is a difference of 2 squares, if you think about it, you could rewrite this denominator as the square root of x plus 3 times the square root of x minus 3 as difference of squares. If you think about that and you FOIL that guy out, it is going to give you x minus 9. So that's just a quicker way, if you recognize that there's a difference of perfect squares there, to rewrite it like that, and then it cancels, and I just have 1 over square root of x plus 3. So now I'm taking the limit as x approaches 9, plugging it in here. Sorry, that's a 9 if you couldn't read it. Square root of 9 plus 3 is 1/6. If you rationalize the numerator just like we had done in example 8, you would have gotten the same exact thing. It's the same process. You would have multiplied, right, your top by square root of x plus 3 over square root of x plus 3, right, from top and bottom. Multiply both of those, and it would work out exactly the same. You would have gotten the same answer. Okay, I just wanted to show you that there's a couple ways to do it. All right, last one. Whoops, sorry, didn't mean to go that far. There we go. A limit involving a trig function and Pythagorean identities. Okay, so again, start with direct substitution, always. But as soon as I plug this in, you're on your denominator, 1 plus the sine of 3 pi over 2. Let's think about that for a second. Here's 3 pi over 2. My ordered pair is 0, -1. So what's the sign is the y value. So it's -1. 1 plus -1 equals 0. And I would have 0 in my denominator. So this one does not work to do direct substitution. Can't do direct substitution. So I got to do some other manipulation. So a lot of times with a trig function, you can remember your Pythagorean identities. Remember Pythagorean identities? In particular, sine squared plus cosine squared equals 1. So when I'm looking to manipulate cosine squared, remember I can just move this guy over. And so cosine squared would just equal 1 minus sine squared. So I'm going to take that whole thing, replace it here. So now I'll have the limit as x approaches 3 pi over 2 of 1 minus sine squared over 1 plus sine. Sorry, these should have x's. Okay, and what can I do with that numerator? Some of you I know already see this. Well, that's a difference of 2 squares. So I can factor it into 1 plus sine of x and 1 minus sine of x. And my denominator is still 1 plus sine x, and look at that. And now I can try direct substitution with the part that's left. So I'm going to plug in here. So that'd be 1 minus the sine of 3 pi over 2, which we just talked about. The sine of 3 pi over 2 was -1. So 1 minus -1. So my answer is 2. And it does work out pretty nicely. Okay, so little tricks. Try direct substitution first. If direct substitution doesn't work, factor, cancel, rationalize Pythagorean identities, try any sort of manipulation you can to get it to a simpler function that then you can do direct substitution. As always, let me know if you guys have questions. Good luck.